I know, I get it. It's on.
All right, ladies and gentlemen, good afternoon. Class recording has started. I just heard a horrible noise because Nicole just moved the microphone. But. All right. The next unit that we get into deals with chemical bonding, like it says on the floor. What we find out, the first units that the beginning units that we've done in this class are hopefully going to start coming together for you. And a lot of the things that we've learned in those previous units we're going to use to explain things going forward from this point. This unit, and today especially, brings in a lot of those different concepts to explain something that we see a lot of. Okay? First, up until this point, we've dealt with atoms. And we've dealt with what is in an atom and how are atoms different from one another. And then we talked about groups or families of atoms and how they're similar to one another. And then we talked about electricity, which deals with separate parts of an atom. Okay? Today, though, if you look at a periodic table, okay, you see that depending on the periodic table that you look at, there are between 115 and 120 different atoms. And each of those atoms is different from all the other atoms. But if you look around this room, can you find more than 120 unique things?
Yes.
Pretty easily. And that's just this classroom. That doesn't take into account the entire universe. So, there has to be a way for those 120 unique elements to come together in a way that produces something new, something with a different set of characteristics than those elements by themselves. Think of those elements kind of like individual Lego bricks, right? Each one of them is different from the other ones. But if you start putting them together, you can make a house, or you can make a car, or you can make a plane, or whatever it is you make with Legos, right? But they're all made of the same bricks. It's just a matter of how you put them together. And that's what we start getting into when we deal with chemical bonding. Okay? So, to get into today, you're going to need something to write with. You're going to need your outline, and then you're going to need periodic tables. So if you don't have periodic table out, grab that out quickly so we can reference it later on.
Elise Kennedy.
What?
Such name.
Thanks.
Got you. Intern, I will say everyone's name in this class before the period ends. Except for me. So no one will know. So no one will know who I am.
I actually said your name before.
Not the last name. No
All
one
right.
knows. No one
Good.
will
Is
know.
it Davis or Davies?
Elise Kennedy.
So, first, by definition, chemical bonds are an attractive force that holds atoms together. This is how we start building new things, because there's something that holds these atoms together and makes them behave in a different way than they do when they're by themselves. But, just like everything else that exists or happens out there in the universe, bonding is an energy process. Because, what did we say our definition of energy was? The ability to do damage, the ability to do stuff, the ability to make things different. Bonding makes something different, therefore it's an energy process. Bonds are going to form between atoms if they end up with a lower energy than they had when they were separate from one another. Bonds will form between two atoms, or more, two or more atoms, if those atoms have a lower energy together than they did when they were apart. A couple of times already this year, we've encountered this idea of things in nature looking to lose energy or end up with a lower energy. For example, this ball. I take this ball and I lift it up in the air. From an energy standpoint, what did I do to it?
You raised it.
I did work on it, and it results with an increased energy, right? Specifically, what kind of energy? Gravitational potential. Okay. Will this ball remain here on its own? No, because it has a lot of gravitational potential energy. Does it like having a lot of gravitational potential energy? No. It falls where its gravitational potential energy will decrease. Okay? If we think back to the last unit, when we talked about charges moving through the battery, right? Where did those charges moving through a circuit, where did those charges start in the circuit? The battery. Specifically, what part of the battery? The negative side of the battery. Because negative electrons, by the negative side of the battery, do they like that?
No.
That's a situation where those charges have a high what? Electrical potential energy. Those charges don't like having high electrical potential energy. So they move through the circuit, and that high potential energy is then transferred into other things. Okay? Some atoms have a high chemical potential energy. They don't like having high chemical potential energy. So what do? They look to get rid of it somehow. Forming bonds is how they do it. Bond formation is generally an exothermic process. Generally. Not always, but generally. Meaning that the products have less energy than what we started with. The two atoms joined together have less energy than the two atoms apart. Because you know English, you could probably tell me something about exothermic, right? The fact that it has therm in it means that it's probably dealing with what? Heat, right? Or something of that nature. The fact that it has exo at the beginning means what? Out, right? Or outside, or something like that, right? So, heat being given off, exothermic energy. A couple units ago, I showed you a video of pure sodium and pure chlorine reacting with one another, right? Do we remember that video? Do you remember what happened when the pure sodium and the pure chlorine reacted with one another? Right? It gave off a huge amount of light and a huge amount of heat because sodium and chlorine by themselves are high energy atoms. They don't like being by themselves. They're looking to get rid of that extra energy. When they form a bond, that puts them at a lower energy state. What do they do with that extra energy that they had to begin with? They release it in the form of light and heat. Okay? That's the gist of bonding. Bonding deals with valence electrons, another concept that we've introduced before. Right? What did we say valence electrons were? Or where are valence electrons in an atom?
The electrons in the highest energy level.
Highest energy level, or Maddie, where are they in the atom? They're like farthest away from the nucleus, right? Farthest, outside of the atom, farthest away. This information on this screen deals with bonding in general. But what we find is that there are different ways that atoms go about accomplishing these things. We're going to start talking about one of them today. Okay? That's what this unit is about. How do atoms go about accomplishing this stuff? Okay? So, first, if we're going to deal with valence electrons, we have to have a way to represent that. And we call those Lewis structures. Okay? Lewis structures are symbolic representations of elements that show their valence electrons. A Lewis structure consists of two parts. It consists of the elemental symbol and the valence electrons that are represented by dots. Good there? So, the first element that shows up on your outline, I'm going to grab a periodic table here.
Madison Mansour.
Yes.
Oh.
The first element that shows up on your outline is what? Lithium, right? So you find lithium on your periodic table. Where does lithium show up on your periodic table? Atomic number what? Atomic number 3. Okay? So here's lithium, right? What family is it in? Alkali metals. What group is it in? 1. We said that all of the elements in group 1 are all similar. Why? Same valence electrons. Specifically, how many valence electrons? 1. So if we're drawing the Lewis structure for lithium, we start off writing lithium's elemental symbol, and then we draw a dot to represent its 1 valence electron. I saw you did that. So there's the Lewis structure for lithium. If I had to draw, say, the Lewis structure for potassium, this doesn't show up on your outline, but if I had to draw the Lewis structure for potassium, what would it look like? It would look like K dots, right? Because Lewis structures show valence electrons. How many valence electrons do all of those elements have? 1. Okay? These all have 1 valence electron. What about these? 2. Those have 2. Okay? Now, we're going to skip that section for now. Okay? Transition metals don't follow the pattern like all the other elements exactly. So we're going to kind of skip over this for now and pick it up back over here at column or family or group 13. Okay? 1 valence electron in group 1, 2 valence electrons in group 2. How many valence electrons in group 13? 3. So 3 here. Yeah, it doesn't really show up that well. Right? 3 here, 4 here, 5 here, 6 here, 7 here, 8 here. Right? And if you look at their group numbers, right? 13 has how many valence electrons? 3. 14 has? 15 has? Okay? The next element that shows up on your periodic table, or sorry, not your periodic table, your outline is what? Oxygen. Here's oxygen, right? Atomic number 8. But more importantly, how many valence electrons does oxygen have? 6. So here's how we draw a Lewis structure for oxygen. First, there's the symbol. Then, generally, this is how we draw it. We start off with a dot on one side. I start mine on the top just because, okay? But then, here's number 2, here's number 3, and here's number 4. We sort of show them spreading out evenly around oxygen. Because remember, that's what electrons do, right? Remember, Hund's rule says that they spread up evenly in the orbitals, blah, blah, blah. Okay? But that's only 4. So now they start doubling up. So there's 5, and there's 6. Generally, that's what the Lewis structure for oxygen is going to look like. Okay? The next 2 elements that show up in your outline are what? Okay. Here's fluorine, here's chlorine. What do you see about fluorine and chlorine? Same amount of valence electrons because they're in what? The same family. Specifically, which family? You remember the name of that one? Halogens, right? And Maddie, like you said, how many valence electrons specifically? 7, right? So, if I go fluorine, right, there's F, 1, 2, 3, 4, 5, 6, 7. Right? If I draw chlorine, what's it going to look like? Same thing, except what's going to be in the middle? Cl. Right? So chlorine, right? 1, 2, 3, 4, 5, 6, 7. Okay. Notice here, in fluorine, I drew my 1 unpaired electron over on the left-hand side, and chlorine, I drew it on the right-hand side. It really doesn't matter. As long as there's 7 dots around it, that's fine. Okay? Then, the last element that shows up in your outline is what? Neon. There's neon. What family is neon in? Noble gases. How many valence electrons do noble gases have? 8, right? So what's neon's Lewis structure going to look like? There's neon, right? 1, 2, 3, 4. 6, 7, 8. Good there? Okay. Lewis structures, a way for us to represent the number of valence electrons, because those are the important ones when we're dealing with bonding. Okay? All right. Why are those important? Because the number of valence electrons that an atom has will determine its chemical properties. When we talk about chemical properties, we're basically talking about what kind of atoms will this atom form compounds with or form bonds with. Chemical properties is how reactive is this atom with other atoms. Will it have a reaction with other atoms? Will it form a bond with other atoms? Remember, the end goal is what? 8 valence electrons. That's the magic number, right? We refer to this idea as the octet rule. Right? The OCT prefix meaning 8, right? Like in an octagon or an octopus or something like that, right? The octet rule says that atoms are trying to get to 8 valence electrons, and they're going to take the shortest route to get there. Why 8? Because what does that mean about their valence shell? It's completely full. Okay? That could mean that atoms are going to gain electrons, or it could mean that atoms are going to lose electrons. It just depends on where they start. If we were to look at and write down the number of valence electrons for different elements, it would look something like this, right? Let me take this here and bring it back to this periodic table, and I'm going to paste it right here. Of course, it's going to go over part of the periodic table, but that's okay. All right, so sodium, right? Sodium, 1 valence electron. Magnesium, 2 valence electrons. Aluminum, 3. Silicon, 4. Phosphorus, 5. Sulfur, 6. Chlorine, 7. Argon, 8. That makes sense, right? Those are the number of valence electrons. But after you go to argon, the next element is potassium. And now we're back to what? 1. So that's what, if you wrote down valence electrons for elements in order, that's what it would look like. But remember, 8 is the magic number. So elements that have 6 or 7 valence electrons, what are they going to look to do? They're going to look to gain a few to get up to 8. But elements that have 1 or 2 valence electrons are going to look to do what? Lose valence electrons to get down to 8. 8's the magic number. How do we get there? Depends on where you start. Okay? Good there? All right. Atoms will either gain or lose electrons to have a full outer shell, or a full valence shell. Like we just said, elements that have 1 or 2 valence electrons are going to look to do what? Get rid of them. What kind of elements have 1 or 2 valence electrons? Alkali metals, alkali earth metals. In general, metals are going to look to lose valence electrons so that their electron configuration will match the previous noble gas. Or they will end up with the same number of electrons as the previous noble gas. Then, just by logic, if metals are going to lose electrons, what do you think nonmetals are going to do? Gain electrons, right? Those are the ones that have 6 and 7 valence electrons. Nonmetals are looking to gain valence electrons so that they have the same number of electrons as the next noble gas. Betty, go ahead.
What about valence electrons of 4?
Okay, valence electrons at like 3, 4, and 5, right? Remember, Maddie, at the beginning I said that this is one way that atoms go about fulfilling those requirements of lower energy and stuff like that. The other way deals with electrons or atoms that have like 3, 4, and 5 valence electrons, and we'll talk about that later in the week. Okay? So yeah, they go about obtaining that octet in a different way. Okay? Generally, metals lose, nonmetals gain. Be aware that it doesn't always have to mean 8 valence electrons. For example, lithium. Lithium's atomic number is what? 3. So how many total electrons does it have? 3 to start, right? How many valence electrons does it have? 1, because it's in the alkali metals family, right? What is it looking to do with that 1 electron? Lose it. If it has 3 and loses 1, how many does it end up with? 2. That's not 8, right? But remember that small atoms, the first orbital that gets filled is the 1s orbital, yes? Does that sound familiar? How many electrons can the 1s orbital hold? 2. Is there a 1p orbital? No. The 1 level, the first level, is full with how many electrons? Only 2. So even though lithium doesn't end up with 8 electrons in the outer level, it still ends up with a full outer level. And that's the important part. So just be aware that for some small ones like lithium and beryllium, right? Lithium, beryllium, maybe boron, they don't necessarily end up with 8 valence electrons, but they do end up with full shells. Good there? Okay? All right. One more, and then we get to the magic. Why 8? Well, we know about noble gases, and noble gases are unreactive. They don't form compounds with other elements. Why?
Because they already have the 8 valence electrons that they need.
They already have the 8 valence electrons they need. From an energy standpoint, Nicole, how much energy do noble gases have? A lot or a little?
A little.
Good answer. Okay. This ball, right? It falls down and ends up on top of these books. Why? How much energy does it have here compared to here? Less energy. Will it move from that spot? No. Not unless I do what to it?
Push it.
Or Joe?
Work on it.
Not unless I do what to this ball? Work on it, right? Okay. Unless I do work on it, it won't happen. Noble gases already have a stable electron configuration. They already exist in a low energy state. So do they have to gain or lose electrons to get to a lower energy? No, they don't. They're already in lower energy state. They don't got to do anything. They're already in that low energy state, so they don't form bonds with stuff. Their highest energy level is already full, so they don't form bonds. Alrighty. Are you ready to witness the magic of modern technology?
Yeah.
There's some pretty sweet animation that's coming up here, just so you know. So.
I feel like it's sarcasm.
Hmm?
I feel like it's sarcasm. It is.
Never.
Alright, so let's talk about this bond formation.
It was sarcasm.
There's sodium, there's chlorine. Do the Lewis structures for sodium and chlorine make sense based on what we know? Sodium, how many valence electrons?
1.
It's an alkali metal, it has 1. Chlorine is a halogen, it has 7. Generally, we know this, right? Sodium, one valence electron. It's looking to lose it. If you look at your outline, Roman numeral number 4, letter A, says sodium has blank. It's looking to blank, right? So sodium has one valence electron, and it's looking to lose it. If you go down a couple lines to letter B, right? Skip 1, 2, and 3. We'll come back to that. Okay. Chlorine has how many valence electrons? 7. What is it looking to do? Gain 1. Right? So letter Roman numeral 4, letter B. Right? Chlorine has 7 valence electrons. It's looking to gain 1. So it stands to reason what's going to happen here. Well, what is sodium looking to do? Get rid of that electron. What's chlorine looking to do? Are you ready?
Take it. But it's not even anymore.
Yeah, okay.
That kind of sounded like the movie thing where it's like, whatever it's called. No.
Who said that?
Oh, what?
Never mind. All right. Now, underneath letter A, right, we just filled in about sodium, okay? Sodium is a metal. Metals look to lose their valence electrons to form cations, not cations, cations.
Yeah, that guy told us that. That one sub. He told us about cation. Yes, he did. Sorry, I forgot his name.
Because cations are formed by elements losing electrons, they end up with more protons than electrons. So they have what kind of a charge? A positive charge. This process of losing electrons we refer to as oxidation. On the other hand, nonmetals will gain electrons and form anions, not anions. Anions have more electrons than protons because they've gained electrons from other places. If you have more electrons than protons, what kind of charge? Negative charge. This process of gaining electrons to form an anion we call reduction. I know that's kind of confusing. You're gaining electrons and it's called reduction. There's a reason why it's called reduction, which we're not going to talk about here. Because you're not ready to handle that just yet.
Okay.
That's right, you're not ready. I said so. Regardless of whether you gain electrons to form an anion or lose electrons to form a cation, any atom that has an imbalance of protons and electrons to become positive or negative we refer generally as an ion. Okay?
Like ion television.
Yes. Good there? All right. So let's apply these terms. Okay? We're only going through page 3 today. All right. So here, after the transfer of the electron from sodium to chlorine. Sorry, I did them backwards. Underneath letter D, this is number 2, right? So underneath letter D on page 3, number 2, chlorine. It now has 17 protons. How do I know chlorine has 17 protons? That's the atomic number of chlorine, right? That doesn't change. But now it has gained an electron, so it has 18 electrons. It has more electrons than protons, so it has a negative charge. It is an anion. But sodium now has 11 protons, but only 10 electrons. Why? What did it do? It lost an electron, right? Did it gain a proton? No, right? right? We said that in the last chapter, when something gains a charge, either positive or negative, it's electrons that move, not protons, right? Sodium has 11 protons. How do I know? Its atomic number, right? Always has 11 protons, regardless of how many electrons it has. That means it has a positive charge. It is a cation. So what is the positive cation going to do to the negative anion? What do positive charges and negative charges do to each other? They attract each other. What's the very first thing that you wrote down today? Go back to the beginning page.
An attractive force that holds atoms
Bond is an attractive force that holds atoms together. Right? Behold. Oh, sorry. An ionic bond is formed when negative charges are attracted to positive charges. Negative anions are attracted to positive cations. Okay? So for number 3, right? Sorry, under, or right above where before it went to ionic bond. Okay? It's just restating the same thing. So up there previously underneath letter D, number 3, right? It says the negative charge on the what? Anion is attracted to the, what is it? And the positive charge on the cation attract each other to form an ionic bond. This results in an ionic bond. Ionic bonds are the attraction of opposite charges. Ionic bonds come about because atoms will transfer electrons in order for everybody to get to 8. So ionic bonds form generally between what kinds of atoms? Metals and nonmetals. Because what are metals looking to do? Lose electrons, and nonmetals are looking to gain electrons.
That's ironic. Get it instead of ionic. Ironic.
That's funny.
That's gonna be written down on the back of my test. It's one of my jokes now. I do sometimes.
All right.
Oh, put the slide.
So just to wrap this up, right? Right. Negative charge on the chloride anion, positive charge on the sodium cation attract each other, form an atomic or an ionic bond. All right, we good there? Okay. Hold on 1 second. Hold on. You're not done yet. So, for tonight, you guys don't have to finish the outline. Other classes do, but you guys did already. But,
Thank you.
underneath Monday, November 26th, first, couple pages from your book, page 151 through 153, deals with ionic bonds. Then, couple problems from the book, right? Right? Part of section review, and then a couple of questions from the end of chapter 5, dealing with bonding and ionic bonding topics. Okay? Tomorrow, we start getting into how to name and write the formula for these bonds, or these atoms that are bonded together.
Elise Kennedy.
Questions
Katie Lou.
as it relates to ionic bonding? Good job today, everybody.
Matthew Plinstead.